המזכ"ל עובד?
מה המזכ"ל?
הוא בטח לא מקרב.
בטח לא מקרב. Somebody fix the air condition. Welcome. The penultimate talk in this year's Colloquium series. I don't think that today's speaker needs much introduction. Professor Shlomo Havlin, the most cited Israeli scientist of all times, as far as I know, joined Bar Ilan in 1972, before any of us were born, I guess. He's still here. Awarded the Israel Prize in 2018. And I just won't mention the other things because it says this is enough. So, please.
Thank you very much. Thank you, Asaf, and thank the organizer for inviting me. And thank you for coming to my lecture here, which is, I want to tell you the story of the last, I would say, 23 years that I worked on. And finally, I think we have experimental proof of the theory that I developed since 2010. On interdependent networks, novel physical phase transition, which is due to our chairman, Aviat Friedman. He did the experiment, but pushing by many others. And the many others include Amir Bashar, who's sitting here. He already started to speak to Aviat on this topic in 2011. And then another student of mine, Michael Bandiger, in 2015. But then came two students of mine, Gross and Ivan Bonamassa, pushed it last year, and finally the experiment worked. And it succeeds to prove the theory that I'm going to tell you today about interdependent networks. So let me give you some review. Actually, this slide is very occupied, but it gives the main story. So I want to go through it and tell you the main story. Then after this, you know the story. If you want, you can continue to say. If not, you can go away. But the story is in this page. So it was before 2000. People studied networks, but they called it graph. It was graph theory. And the main people that worked on it were Erdos and Reini. They developed, Erdos, the famous mathematician, developed, also Euler worked on it before, but Erdos worked on it systematically and found the theory for these networks. He assumed that the networks are random. It means every node is randomly find another node and make a connection between them, have a link. And the degree distribution, which is the number of links per node, was Poissonian. Poissonian means that you have some average plus minus some changes, but small changes within the average. And then, this was before 2000. In 2000, when computers start to work very efficiently, already, not compared to now, but compared to before 2000, and we could analyze networks through the computers. And one of the networks that was studied was the internet. So three computer scientists, three brothers, Faluzos, this is the name of the paper, Faluzos. They wrote a paper in 1999 saying that surprisingly the internet is not Poissonian. It's more like a power law distribution, which means that instead of having a characteristic number of links per node, like the average plus minus, you have a power law distribution. They did not mention power law, but the figure that they have looks like a power law distribution, because you have also many nodes which have only one link, but you have nodes which have many links, and this is represented by power law. You can have also large degree. K is the degree, the number of nodes, the number of links per node. So, and this was a breakthrough. When we saw this paper, I came to my student, Ruben Cohen, who was here, and then we realized, I told him that, let's see, because of the change of symmetry from here to here, and the break of symmetry here, what is the symmetry here? Every node sees around him almost the same neighborhood, 2, 3, 4 neighborhoods. But here, there is a big change. Some nodes see a big neighborhood, like the red hubs. They see a big, many, here you have small. So maybe the physics will change, and indeed we put into physics and we realize that you have new results which could explain many phenomena that could not be explained here. For example, why viruses spread in the internet, although enough people bought antivirus. It was not clear to the computer. This was a big question in computer science in around 2000. But after we realized that the network is not this, but the network is this, we realized that you need, in order to stop the viruses, you need 99 or 100% of the nodes to be immunized, which of course was not true. So this was in 2000. But here was the story, and since 2000 many people studied networks, but they studied networks which are scale-free, which call it scale-free because scale-free means like you have all kinds of degrees. You have degrees, small degrees, medium degrees, and high degrees. High degrees means that you have a node which has many, many links. And these studies were very efficient, but it was single isolated networks until 2010. From 2000 to 2010, there was a big breakthrough in networks, but all of them studied single networks, and they could be useful in many disciplines, but not in physics. There was no physics. You see, the disciplines were climate, social network. I didn't write here, but there are many. There's no field, almost scientific field, that network was not useful. And we found new concepts, but you see, all these are not physics. And I was wondering, can we also learn something from networks about physics? But I could not find also for here anything. So in 2010, actually for 2009, I was in Boston, and I came to us some officers that control the research in the army, of American army, and they told us, look, you have some, it was 2009, just before 2010, they say, look, you study and you have beautiful results on single networks, but networks are not isolated. Networks connect to other networks, and they depend on other networks. And if you study, you may miss a lot of information. So, and they told us that network can depend on other networks, like for example, a power grid. It does not stand for itself. Before 2010, we studied power grid, only the power grid. We didn't study how it connects or depends on other networks. So, and you need communication, you need transportation services. Indeed, it was justified by this picture. Look, in 2001 already, engineers wrote how interdependent are infrastructures. The power grid, you see, is not standing alone. It depends on natural gas system, depends on water, on oil, on telecom, and everyone depends almost on everyone. So the world is much more complex than a single network. So it was a need to have a theory for networks of networks. And then I became, in 2010, with a paper that was published. This is the paper in Nature, that appeared in 2010, where we studied a model for network of networks, like this. But the unique and the interesting part was that instead of having only black links, which are the function of the network, the black links here, assume this is a power grid, the black links are for transferring electricity from one place to another. And for example, communication or transportation or other services. So all of them, but they are all depend on each other. So we introduced a new type of links. New type of links, which are the red links, which are dependency links. When I introduced them, I was sure that already people did it before, and it took me years to realize that nobody did it. So when you introduce the new links, these are very different links. The links here means that if a node here does not function, automatically this node doesn't function. We can do it in one direction or two directions, but we can see new phenomena here, which we did not see here, which means cascading failures. Means failures here lead to failure here, lead to failure here, failure here, back to failure. It can be cascading failure between the network. Actually, when I introduced these two types of links, it was people did not accept it so well, and many people attacked me and said, "What is the difference? It's almost the same." And even it was very difficult to convince people that the links are very different. And in the links, if you think about it, you can understand that the links are very different. For example, even if this node still connected to the network here, but because of this node, it cannot function. So it's a dependency. I depend on this to get function. I cannot. And then when I started in this, in 2010 to work on this, which was published in serious paper here. This one, this Amir Bashar is here, a very nice paper, I will speak about it. And all this, up to here, up to 5. We had a lot of interesting results on this, and there are many more papers on interdependent network, which means networks that depend on each other. And then I came to Aviad in 2011 together with Amir Bashar, and we said, why don't you do an experiment that to take, we knew about is one layer experiment, superconducting networks. It means that if you put here a voltage below DC, it is a superconductor, but above DC it becomes a conductor. We suggested him to put this and another layer here, and which means like two networks, like here we have two networks, and the two networks will depend on each other, not by electricity, but be put in between an isolated material which isolates current, which isolates electricity, but conduct thermal heat. So it means it's another interaction. And the heat, why the heat is important? Because if one of the superconductor becomes a conductor, it heats, and then it will transfer the heat to the other layer, like here, dependency between the two nodes. And indeed, we started to do this, as I told you, in 2011. We spoke to him, he tried many things, and then this Michael Danziger in 2015. My student worked with Aviad a lot, and I tried to meet him. And only when we came in 2021, we started to see the results which are published in 2023. Just published in May 1, 2023, that we could realize, make an experimental system in which we can see effect of interdependent network, cascading failure between the system, which means heating here leads to heating here, and you see a new phase transition that we could not see before. And what we learned from this, and this is another step important, from all this interdependent network we can understand now, to my opinion, much better phase transition that we worked on it for 100 years. And 3 types of phase transition. I will show you how we can understand, because they appear in this system. A second order phase transition, which is a continuous transition. It means I change the parameter here, and the order parameter goes up a transition continuously, like in one layer. And then we can understand mixed first order transition also. We understand the mechanism. What are the mechanisms that controls the first order, second order, and mixed disorder? And more than that, we find a new phase that few people didn't know before, where you can interrupt the system microscopically, not macroscopically. Layer changing P means macroscopically change. You interact, you interfere, you make interference in the system microscopically, and it leads to a macroscopic phase transition. It means I can change in one place, any place in the system, for example, it somewhere here or anywhere here, and this will lead by spontaneously to phase transition. I will show you later the result. Of course, the experiments were not done in all the regime, but for some of the regimes. So these papers are a set of papers where we have some results. So as I told you before 2010, there was only single system, and justify why we need system of systems, because system depends on each other. And we see here how they depend on each other. We see here that all the systems must be dependent. And so what to do? So we started in 2010 to take dependency between systems, to take dependency between networks. And the simplest case was, or before this, let me just show you another case where you see that the interaction between systems is important. This is it was a famous blackout in Italy. I had a student here, Ivan. He was a child. I remember this day. In Italy, everyone in Italy remembered there was no refrigerator and no traffic. It was like in the 2000 years ago. And they could not, and this is what happened because of the interaction, dependency between the power grid in Italy and the communication which controls the power grid. There were failures here in the power grid, which lead to failure in the communication, and back to the if you don't know how to transfer the electricity, then you are not the power station cannot work. So this was well documented in this paper by Rosato Engineering, where they saw that you can see what happens because of the damage. Italy broke to two, and they could not transfer the electricity, and then they stopped the electricity in the country. And the same happens, similar happens in Japan and hurricane 1 year, less than one. That was it in September 22, Hurricane Yan. Of course, one damage in one system, electricity, leads to damage to other systems like the transportation, like communication, and many other systems. And they call it cascading disaster in Japan. I remember this day I gave a talk in Boston, and I went from the hotel and I saw this. I said, let me make a copy of it, show it to the people. So the same day I could make a copy of this figure and show cascading disaster in Japan. Because of the cascading between the system, because the dependency of the system, they lead to cascading failure. So let me remind you a little bit about simple phase transition, percolation, and from there we go on a single network. This was on a single, what we know already for many years. For example, we know already for random network, there was a formula, exact formula by Erdős and Reini in 1959, where they solved this problem analytically, which means this is a network, a random network, and now you start to remove, if let's say if P is 1, P1 means that all the nodes are in the system and the links are in the system, then P infinite, which is called the relative component, which is functional, is 1 also. It means that I can send a message from here to anyone in the system. I can go from here to anyone. I know how to go, and I can reach everywhere in the system. Now what happens if you start to remove randomly 10%. It means instead of 1, you have 0.9. 10% are removed. 0.9 means only 0.9 of the nodes are intact. The other 10%, 0.1, I remove randomly. And then, of course, the network becomes smaller. First, those that I remove, but there is also another effect. If I remove, for example, this one and this one randomly, this one is also not functioning. So it's not linear, and it's a phase transition. It's a very simplest example of a phase transition. And phase transition in such a way, you should see later, you have critical exponent, you have all the phenomena which you have in phase transition. More than that, Erdős and Reini succeeded to find the analytical formula for this quantity as a function of P and as a function of K. K means the degree of the average degree of the node. The average degree, if it's 3, you put here K equals 3. And this is analytically, and it's exact. For lattices, we have also solutions, and this is also since 1980. You can see if you have a lattice like this, this is random, and this is space. It's very important because I'll show you later that space is crucial for many new phenomena. So for P below PC, like 0.2, 20% of the nodes are occupied. Occupied means black, and you see small clusters, cluster of 5, cluster of 1, cluster of 3, maybe, or 2 here. But when you have P.9, you see that you can have a big cluster and only small empty places here. And the big cluster, for example, if these black are conductors and the white are isolators, it means current that I will put from here to here will not go through. But here, if I put current, voltage from here to here, there will be current here. But there is a critical P, which is in this case PC critical 0.5, in which you have just a connection between the two layers, you see between here and here, but just below it, it becomes 0, and above it, it appears. So this is a type of geometrical phase transition. And these are the critical exponents, and the distribution of clusters is this, and the giant component near goes to P minus P to the power beta, and correlation length, susceptibility. So everything can be studied on simple model like this. Now we want to go to extend this to many networks, to interdependent networks. So what we do is we take now, instead of looking on one network, as I said before, I look on this only. I look on a network of networks. It means this one, each point, each node is a network. This one is a network, this one, but they are depend on each other in the way that you see here. I mean, nodes from one network depend on node the other network and vice versa. The same here. Now I can put it any way, like this, any tree structure like this, and I can get an analytical formula to what will be the giant component after removing one minus p of nodes. And we solve this analytically, and we find that P infinite, the giant component, goes like P times the same to the power n. So if you look on this, and you look on the old formula of 59, you see very similar. The only difference that here, you don't have n, you don't have anything, but here I have n. So for n equal 1, I get the solution that is known already now 64 years ago. But for n equal 2, I get new solutions. I get, solving this equation numerically, I get jump here, and the jump here, abrupt transition. And you can see that, so this tells us that indeed, what we studied in many years was only single network, but the generalization of many networks is this, and they behave very different from this network. And the reason for this is, when you look on this, why you have a jump here? Because of the dependency, you start to have cascading between the system, and the cascading drops the system. If you reach a certain value, enough cascading, and the system drops to 0.
Shlomo?
Yeah.
Is it possible to write a field theory for this?
People write a field theory. Yeah.
And it has the first order transition as a...
Yeah, I think so. Yeah, they have a formula. But maybe we can discuss it later.
Shlomo,
Yes?
I have a simpler question.
Same question?
Simpler.
Simpler.
I mean, you add the red links, so I would guess that you have one new parameter because you have P and
Oh, you're right.
So-
This is, okay, good that you found it. I wanted to, okay, this is the case when Q is 1. Q is 1 means that every node in one network depends on every node. But Q can be a parameter, I will show you later. You can have dependency, not everyone depends on everyone, but because if we took here Q1, we could solve it analytically and see what happens. The phenomenon is the same if Q is not 1, I will show you later. But Q1, you can get a beautiful formula which reminds us this, but you see what happens here, and Erdős could not put here n because he solved only one network. So that's why we can regard this as a generalization of Erdős-Reini that we found in this paper, in these 4 papers. So let me go further. Yes?
In systems with multi-spin interactions or hyper-edges, one can find also in one system first order.
Yes. I will speak to it. Okay. Yeah, he's right. If you take, I want to say, I think I want to relate to this, what I told you now, that you need two interacting systems like this, because what I took here, I took this image network, like here, connectivity links between the network dependencies. But we showed already in 2011 and 12 that I think even Amir showed it, Amir, in his PhD, that if you take a single system and you introduce another interaction, dependency interaction, which means that this node falls not only because it is not in the network, but also because another node, let's say this one, it depends on, you will see the same result. You need two interactions, not on two networks, but because we have two networks, we can distinguish between the two interactions. One is in the network, one we could not see it if it was in the same network, but we can prove it analytically that it's correct what you say. And this is related to you. I believe that in many systems that we saw phenomena like first order and mixed disorder, are coming from similar origin, that you have two interactions. And this is related to your question. If Q is not 1, we have a Q critical. Q critical means Q means the fraction of nodes in one network that depends on the other network. QC is 0.2. It means below 0.2, you have like 0.1, you have a continuous transition. When you are above 0.2, you see abrupt transition. So it means how much you depend on each other is very important, and this Q critical is also very important. But let me show you more than that. If you take now loops, I did not take loops into account. Loops, you see, this was the solution when I don't have loops in the system, which means I have only line or a star or just a tree, but no loops. When I have loops, I can also generalize my formula and find an analytical solution, which was published in Nature Physics here in 2012 by actually now he's a professor in America, but he was a student here in Bar-Ilan. He was sitting here. I don't know if you remember. Maybe Amir remembers. Yankee Gao. So we solved a more complex system, like having here a network of networks. Again, each network is like this. It's given K average degree, L-Bashreini network. But each network depends on not on all networks, but on the same number of networks. For example, in this case, n equals 3. Like this one depends on 3 networks. This one depends on 3, this one, each one depends on 3 networks. So here you have loops. Can we also do the same analysis? And we find analytically a nice formula that gives you how the giant component depends on P, how it depends on K average, now also how it depends on Q. Q, the fraction of nodes in one network that depends on the other network. It means I can take it 10% of the node, depends on 10% of the node here, and vice versa. And I can solve it analytically. And analytically is very important here because if you solve analytically, you can follow deeply what is going on in the analytical equation. Yes?
I mean, one can see there that essentially with increasing M, the transition moves to higher and higher values of P. So the right word. So the question is there some kind of a value of M where basically it fails automatically?
Yes. Depends on K, of course. Depends on the degree, of course.
So there is always a value of K. So there is the limit to possible complexity, because otherwise this will not function.
But here you see it's a more complex formula, but so, not surprisingly, if you substitute n equals 0, which means a network does not depend only on 0 networks, not on 3 like here, or q equals 0, the nodes here do not depend. So either you put m equals 0, and then I see this becomes 1, and this becomes 1, and what is left here is exactly what was obtained in 1959 by Bashreini. If you put q equals 0, you see almost the same. This is 2 to the m, 2 to the m cancelled, and you have again the same order. But here you have also QC. It tells you how much dependency you can put, and it will be still second order, and above it, it will be a first order transition. So, so what? So we found analytical formula in this, but can we go into it and look for the mechanism? What makes it like this? Why here we have a continuous transition for single network, and why when you have a coupled network, you have a jump, first order transition? And this was in a paper, we started in a paper by a Chinese student that was here, Zhu Dong, and joined then Ruben Cohen for mathematics, and Nadav helped me also, Nadav is here. And we published this paper. It was so surprising that, when I did not try to publish it in a good journal because I know there was rejection and people rejected it, so I published it in a simple journal, PRE, but I think it was very important step to understand the mechanism. What we looked here is what happens when the system breaks from here to here. As I told you, I have two networks, and let's say dependency links are the red links. Node here depends on this, and vice versa, or without vice versa. And what we realize when we look on this jump, here I magnified the jump here. If I look on this jump, this is the same as this jump. What we see is that a new critical phenomena that can be observed. The system goes from here to here, not just from here to here abruptly, but it goes through a plateau. What does it mean, a plateau? Let me explain. It means if I follow the damages here, that lead the damage here, and back, for example, this I call 1 unit of time. And then, but new damages here lead to new damages here. It's another unit of time. And new damages here finally brings to more damage and more damage. And during these damages, the giant component of the system does not change much. It's very little. What does it mean? That in between, you have a microscopic process during the transition. During this transition, you don't have a jump, but you have that some damages, few damages here, little damages here, and few damages here, and this doesn't break the network until it reaches a size which is the order of n to the 1/3. It's a macroscopic time. It takes time to reach this. And during this, you have only a branching factor which is 1. We measured it. Branching factor means 1. That the nodes here makes the same number of nodes. Few nodes here make damage here, and few nodes here make the same damage, similar damage here. And it's like a branching, like to say that the process during this jump is at criticality in the sense that like epidemics, that one infect only one person, and one person infect. Like in R equal 1 in epidemic, that we already, I hope you still remember. So this is what happens here, and this criticality is represented by two critical exponents. One is the tau, how long it is, depends on the system size, 10 to the 1/3, and tau, how close you are to criticality. You can be here, either here or in the range here, and the closer you are to criticality, tau is longer. And I will show you later, this is exactly what you will see also in the experiment.
Shlomo, in Erdos Reini you have also the same double jump. Erdos called it double jump, that you have a transition from 0 to maximal component, which is...
Yeah, but this is a different story. The jump that Erdos is speaking, that at criticality, here, I will show later, at criticality here you have not a compact cluster, but a fractal cluster. I will show you soon. Soon you will see it. So now, so what? So we have now a better understanding of the dynamics, but can we learn something more? And here I won't go much into it. We show that, for example, that we can understand better what happens here in terms of critical phenomena. So one thing here, that if I look on this exponent is called, it's mixed disorder here. We call it it's not first order, it's a mixed disorder because you have a critical exponent also here. It's beta 1/2. If you measure this, beta 1/2. But more interesting is what happens to PC and what happens to the giant component here. So they fluctuate from system to system. PC fluctuates like a Poisson, and the Gaussian, and the giant component also fluctuates every realization. But why is this important? This is very important because when I published the first papers, many people attacked me, I told you. One of the persons that attacked me, he made simulations and he found that it cannot be a first order. It cannot be a jump. It must be a continuous. He even said he has a mathematical proof for this. And what did he do? He took each realization, all realization together. Because of the fluctuation of PC and the fluctuation of P infinite, if you average over many systems, you will see a continuous transition. And he published this paper, attacked me very much. And then in a conference, in a paper I wrote that you should do it carefully. You should do a single system. If you want to measure this exponent, for example, you must average not on the system, but also on how far it is from your PC. Not how far from the average PC, how far from your PCs, for the realization PC, and then you get all these results. So let me just say that we generalize now to the understanding of this type of transition and this type of transition. Why you have a critical and critical is very interesting, and this is written here. Actually, we have here measurements, and we show that you can have a scaling for all these parameters in many dimensions. This was done by Bnei here, I think the Bnei gross. And what is interesting that you have also here, if I look on this, if you remember, I told you that, or I updated it, that here it was found that criticality in any second order transition at criticality, the giant component is a fractal. This is known for many years. But what happens here? So what happens here is not the giant component of the fractal, but the fluctuation of the giant component of fractal. And this is the new thing with the same formula. You can prove it that it is indeed the same formula. You have a fractal dimension. You see the fluctuation of the MC. MC means the size of the giant component here. So the fluctuation of the giant component is a fractal. And the formula that you get is identical to the formula that we find for second order. It means now second order and mixed first order, mixed because you have critical exponent, are of the same origin. The same critical exponent, not the same critical exponent, but the same scaling relation can be shown for both. So I will not go into it too much, but then, yeah.
Maybe I did not understand, but you mentioned that you're not allowed to average, if I understand correctly.
Yes.
So, but
if you average,
no, but let me ask the question. But then, let's say you have a single system. You add P, let's say in a percolation, then either you are transmitting or not. So it's 1, 0. So so I don't understand the concept of.
I will explain. Instead of averaging P infinite, you have to find for each realization its own PC. And then you average how far you are from PC. So every realization has its own PC. Now you take, let's say, 0.01 distance from PC, then you can average over its own PC, because its realization, by naturality, each realization has its own PC. So if you average over P infinite, you will see kind of continuous transition. Now I think it's very clear. Now let me show you now what is next. So what I showed you before, everything was related to random networks. You see random networks without space. And we understand now the mechanism of why it has such a jump and how it goes, this jump. This jump goes because you have interaction between the layers, which are very, very few interactions, and it takes long time of order macroscopic time to make the transition. Now, the question is, what happens if the system are in space? Spatial networks, right here. Spatial networks means that I take, for example, two lattices here, another lattice here, and I make dependency between them like this. R equals 0 means the dependency is at the same location. This one depends on this one. R equals 2 means that this depends on this one, which is 2 units in the XY axis away. And now I can control the dependency by up to a certain distance. Let's say if all R is equal, if R is equal to 0, then I plot it here. PC is this point, R equals 0. This point is like a single network. Single network because if a damage they make here and all R are only in the same unit, the damage here will reflect the damage here, but there will be no cascading. It will not come back. So already R equal 1 leads you to PC, which is higher and higher and higher. This is the limit, up to R equal 1, up to R equal 2. But then you reach a certain point in which the system changes its behavior. The transition here is continuous, and here it becomes abrupt. And the question is what happens here. And this is, I will show you that there are new phases here that we did not recognize before.
But what is the Q? What is the Q? I mean, how many?
Oh, here Q.
Is it important?
It's important, of course, but the Q, let's say, is high enough that you have dependency, above the critical Q. I don't care now about the Q. So what happens here? What happens here? So I told you this is the phase diagram, and I wanted to look what happens in this question mark, in this regime. And this paper, this work, we found, by if you look on the full phase diagram, this is actually the same as this one. Below this point, it is unstable. Above this point, it is stable. But this is the question mark, is the yellow regime. So we find a new phase, which we call metastable regime. What is the metastable regime? The metastable regime is enough to make a damage in one system of a critical radius, and this will make the phase transition. It will lead you from here to instability. From here you need a bigger size, from here smaller, smaller, and smaller, and here small size. Does not depend on the size of the system. You can have an infinite system, but make a small damage here, and the reason is because of the relation between the size of the hole, the size of the damage that I make, and the radius of the distance. It means I have a characteristic distance that the damage can spread, and it spreads into the system and brings me, if I look on the system here, just here, without making damage, it looks like stable. It's all the system. But if I make a damage of certain size, it will spread into the system, and this is very catastrophic because you may destroy, for example, infrastructure. If you know the characteristic lengths of the dependency, you may destroy them by making it in one place a damage, and this damage will spread. As you can see, for example, in this figure. Look, here, this is the power grid of Europe. Power grid of Europe. If I make random damage, it does not spread, but if I make localized damage, it spreads into the system and can break the system. Because I have another length in the system, the length of the dependency, and this brings the damage farther and farther and destroys the system. More than that, if I am localized attack, you see, it does not depend on the size of the system, but if I have a random attack, you see it depends. So it means I can damage the system by microscopic interference, the intervention. I make an intervention, a microscopic intervention, and change the system.
What is the localized attack there at Ukraine?
Oh, no, I didn't. Okay, just anywhere. Actually, you don't need to make the localized attack here. If there is a characteristic scale, anywhere that you make it will spread. Like here, you make it anywhere in the system, it will spread. Why? Because it's very easy to understand. I make a damage in one layer. Because of the dependency in the other layer, it can become a little broader. And then back and forth, and in this way, it will spread into the system, and you can have a phase transition. Phase transition by controlling microscopically the system. Now the question is, can we apply and prove the theory? Up to here, it was just a theory of interdependent networks, percolation, just abstract geometry, not real physics. There was no physics in the system. Just the question is, what happens if you have, yes?
So I have a question about that, just to clarify. You're assuming that each node in one layer is connected only to a single node in a different layer, or
yes,
multiple nodes?
This is the simplest assumption, but people already extended it depending on several. I mean, what I show you is the simplest example that one can solve easier, but people already did extensions to other systems, and the phenomenon is qualitatively the same, only quantitatively different. So can we apply and prove the theory of interdependent network? What I showed you before, that I have a rich phase diagram of first order transition, second order transition, mixed order, and by microscopic I can do it also in real systems, in controlled physical systems. Why I need it? Because in worldwide systems, which I think the theory should work on the internet, as I showed you, on power grid, I cannot control, I cannot change dependency, I cannot change the connectivity. They don't allow me. Even now, we got a grant from Chabad Hashmal in Israel, the electric company, but they don't want to give us any data. They say, you work on models, not on data. Because data is secret, they don't give us data.
They don't have data.
But at least it's not easy to get real data in order to find how the dependency works. But so let's go to lab, where I go to Aviad Friedman. He tells me exactly what is the connectivity, what is the dependency, and he can change things. So can we do it? And to do this, as I said, we involved, I worked with Aviad, my student here, Sanaya, and Ivan is now a postdoc. And before I worked with Mashan 12 years ago, and Ruben Cohen, not Ruben Cohen, it was Michael Danziger. And we found that we suggested the following. He worked a lot, Aviad, on single layer superconductor networks. Like this, you put a voltage or electricity, current here, and then below TC, each layer. This is two layers. One layer is superconductor below 1.7, you see, or this one is below 2.5, temperature 2.5, above it becomes a resistor. So because of the elements that you have here, which are superconducting elements, each one has another TC, it's a distribution of TC, and we found this. So as we said, let's put them together and put in between a thermal conductance layer, which we did, and electric isolator. I don't want that it will be connectivity link. I want only dependency link, like before. And this was very difficult to convince people that dependency and connectivity are different. Even my friends, they didn't believe it, that dependency and connectivity are different. So now I think the experiment already convinced some of them. So if we do the theory for single layer, this is the experiment, and Naya did the theory here. You can ask him the detail. And look how nice the theory for each layer is the same, similar to the experiment. It means you have a superconductor below and a conductor above. And we solved the Joseph conductor, the Kirchhoff equation you need to solve, and to find, you can find this phenomenon. Now, what happens when we put them together, and in between, we say we have a thermal conductor, conductance, electric isolator. So instead of these two continuous transitions, you see before I showed you also, this is the two layer, each layer by itself is a continuous transition. We get instead the two layers an abrupt transition. And the abrupt means it reaches a certain point and jumps to superconductor. It reaches a certain point and jumps to become conductor. Actually, we can see hysteresis. It becomes one system where each one behaves slightly different, but both have the hysteresis that you see here. It means that you go, you jump. And what happens in between? And the question is, as I showed you before, what happens between is that the system does not go like in percolation. It doesn't go dramatically from here to here, but it reaches a certain point, it stays long time at this point till it reaches here. Until it reaches here. And if you remember, I showed you also analytically in percolation that the time here, that the time goes like P minus Pc to the minus 1/2. It means the closer you are to the criticality, the plateau is longer. And this is the measurement that Avia did. I hope it's not angry on me that I put it here.
Ira did it.
Who did it?
Ira.
Irena? Irena, is she here? Irena. Where is she? I see it here. Very good, Irena. This is excellent because we see here that the power 1/2 is shocking. You see, almost 4 orders of magnitude, we see the power 1/2. It means that the length of the plateau that happens is exactly what we find. The reason why we find like percolation, I understand it, because the dependency makes it like the same system. Because it's dependency mean field, everyone can flow the heat everywhere in the system, and it's not like the case where I showed you before that I have here a certain R. I'm looking only in the range where R is everywhere. It means it can come everywhere. And that's why it's kind of a mean field result, but beautiful 1/2. She did it several times, and they found 1/2. We did not publish it. It's going to be published soon. So I think this is the main proof that we can see a critical phenomena in the experiment of Aviad here, that this time, how long it takes, it follows the theory of interdependent networks. Yes?
So the picture is that you have, say, some conducting link that heats up this layer between them, and then it heats up the whole system.
You see, I think it's the same. But you see, you remember that each superconductor has its own TC.
Right.
So if it eats, it must find somebody, some superconductor that has a close disease, and this becomes, it can be far away, and it becomes
I guess,
conductor.
but it, like, I would assume that it can also work in the plane, not
In the plane, yeah.
So then you could do it just with a single layer. Why do you need to?
I told before that we found already in 2011 that the single layer is the same, but here we can control. We can control
The distance.
not only distance. We can control the distance, but we can control that you have only dependency between the layers and only connectivity within the layer. We can control the two interactions, which we cannot control if we have one system. But in one system, the phenomena that we see and we get, like Ido said before, you get a mixed order. It comes, to my opinion, more and more evident. It comes from two types of interactions. Yes.
The formula p minus pc to the power of -1/2, I guess it's only at the vicinity of it's a transition zone. Say.
Yes, it's a near criticality.
So how come that the transition zone is so wide? You have 4 orders of magnitude of a parameter within the transition zone.
Maybe the range of I don't know. We have to ask, but I think you did not. We need, in order to see, to answer the question, we need to see how R changes I. Maybe the range in I is much larger, but here also you see the transition zone looks quite maybe almost half a degree. You see, so maybe here it's 10 ampere. This is 1 ampere. What is this?
Yeah, it's in ampere. The units.
What are the units?
Microamps.
Microampere? Okay, microampere. So it's
But,
not so
but the
big.
4 orders of magnitude are the current, right?
No, it's different in current. No. I think it's a good question. I have to check. It's different.
This one's in current, yeah.
Yeah, it's not different. How far you are from IC? But IC may be very large. So IC is very large. Then if you are 10 microampere, you say?
IC is about 100 microamps, and you get to about
Up to 5, 10.
But it's known that quantum calculation PC is much higher than the classical one.
Yes.
So this might explain this range. For instance, Anderson transition occurs much higher than classical calculation.
Yeah, could be. Now, so what we have here now is indeed the theory also fulfills exactly what we see in the experiment. You can see here, this is the theory, and this is the experiment, and you see both abrupt transition when you make them together, when you put them together. So what do we learn? Actually, we have what I want to tell you now, what we expect in the future to do. But let me first summarize what we saw already. What we saw already is that what we did for many years was only single network, and we looked only on this transition. When we look on, and what Avia did is actually when R, the thermal range can be infinite, and we see this transition and we see the plateau here. This is the range of plateau. But if you now take a thermal range, which is, if you can make an experiment, what is not going to do, that the thermal range will not go anywhere, we will see a much richer phase diagram like what we see in percolation. That's what I expect. And we will see a metastable regime in which, if in the thermal range is a certain size, in which you can go from a superconductor to normal by just making a microscopic change of certain size. Like here we say we have damage of certain size and you go to the unstable state. Here the normal state will be small, and then it will go here, and the more you're closer to the normal range, you need a smaller and smaller circle. So finally we have 4 types of transitions. 3 that we already observed experimentally. I'm sorry, no, we observed experimentally only this one, and this one, the continuous and the abrupt, the mixed disorder. We expect to have this localized first order, which comes when you have a metastable regime here, in this regime. And what is interesting, what we see is that what we expect in the future that microscope, as I said, microscopic will yield macroscopic transition, and this will occur in the whole metastable regime in this regime here. So let me just summarize. I think we have time for questions. So first I showed you generalization to network of networks. If I have n interdependent networks, I have a formula which is generalized. This was done already 10 years ago. And we have new paradigm, abrupt collapse versus continuous. Instead of a continuous second order transition, we have abrupt collapse here. Because of here, you can see it here. And study this analytically helped us to understand what the plateau that we see here. The plateau is a microscopic interaction between the system. And then the main advantage that I show you today is the back to physics lab, interdependent physical networks. We generalize the phase transition, see microscopic interaction between the system. Here, this regime you see here, it means that when you reach the system here and they are coupled, you have an interaction which is microscopically going up or down depending on the if you're cooling or you are warming. So I think we have now a new view on the general phase transition, why we have a second order, why we have a first order, when we have a mixed disorder, and when you have a microscopic intervention that could yield a macroscopic regime, macroscopic phase transition. Another new regime that I hope in the future, we see it now in simulations, but hopefully we will see it in 1 or 2 years also in experiment. Thank you very much.
Okay, thank you very, very much.
Can you use the metastable state as an amplifier in single photon detectors?
This is what we are thinking about this, because a detector will be very sensitive, because in this case it will not just change the state a little bit, it will change it dramatically from one state to another one. So this is why Moshe is here, trying to help us next to this.
Yeah, but the temporal response will be terrible. The temporal response will be terrible.
What is it?
The temporal response will be terrible.
Yes.
Because it takes a long time to capture the system. It does, but it takes a long time.
But if you do it, how to say, in a small system, it will be faster.
Yeah, but then you lose the sensitivity.
No,
I mean,
only if you're on the
okay, you need to, I agree, you need to play with it.
In the metastable case, it's spread out linearly in time.
You're right. The metastable, so it's spread out like one square root of n, like L, like the size of this system. Linearly, it will be faster, not essentially.
Yeah.
I have two questions. One is that you have two types of interactions. One is attractive, then you have the red one, which are repulsive in some sense.
It's not perhaps as attractive. I think
it's to shut down, the activity of the other node. So to get a metastable, it's like you take a mixture of ferromagnetic and antiferromagnetic interactions, so like in spin glasses. So this is the first question. The second question is, I think this is the major question, is if you can observe all this type of phenomena in one system, so why not to look on these networks of networks as a layer of the same system with some annealed approximation. So again, if you can observe that all this type of phenomena in one system is two types of interactions, so when you look at system of system, it's like one system is feeding another system. What we call in physics is D+1.
yes, but the reason why we do it, I explain again, is because in one system, in experiment in particular, you cannot control the two interactions. In two systems, you can control. If you put isolator, electric isolator, you know that the interaction of the current is only in one layer, and the thermal is only between them. So that's why we can better make this
Fundamental concept.
Fundamental concept. I think what is important, what we found here, that when you have two types of interaction. Let me say, maybe I didn't say it clearly. If both are short range, you will expect to see